All right, to pick back up kind of where I left off. Wavelength is what again? The distance between two waves. Now and again, you kind of already defined this distance between two waves. What are those two distances mean? Or where are the parts of those waves? The trough to trough, which is the bottom, or crest to crest, which is the top again. So the optimum wavelength, again, that means the best wavelength for the measurement of this thing. Now again, do you have a name for that? Or it's iron, and y'all don't know what that SCN, that's thiocyanate. This is just a complex ion, is all this is. Must first be determined. Now let's talk about that. Let's read it one more time. The optimum wavelength for the measurement of that must first be determined. Now let me just kind of go into a side note. What is the only part of the electromagnetic spectrum we can see with our eyes? It's called visible light. Fantastic. What is that acronym for all those colors that we can see? There you go. Roy G. Biv. Now we're all on the same page. Roy G. Biv, which stands for what? All the colors in the rainbow. Very good. Now, the part that I want you to understand, remember, this is the only thing that our eyes can see. What is to the left of the red? Does anybody know? Infrared. What does infra mean? Infra means below. Very good. Infra means below or beneath. All right? Infrared. Can we see that with our eye? But can you see it with the aid of a tool? You remember me showing you this? You saw it with a camera. You could see the light bulb. It actually works. You remember that at all? Okay. All right. So we can see infrared. We just need some help. What is beyond violet? Ultraviolet. That's the good one right there. So we have ultra, all right, UV. Now, which one of these, infrared or ultraviolet, is more powerful? How do you know that? That'll tan your skin. Okay? So if we know it's more powerful, there was two characteristics or qualities of a wave or electromagnetic radiation that we really focus on. Wavelength is one of them. What's the other one? Frequency. Very good. We have wavelength and frequency. Since we know UV is powerful, what does that mean about its frequency in comparison to the frequency of infrared? Okay. First of all, what is frequency? Like how many times it goes in one touch. Okay. All right, hang on. There's number one, it's not speed. Why is it not speed? This is all light, and all light travels at the speed of light, which is what? Anybody know? 300 million meters per second. 3 times 10 to the 8th. Okay. You said something. What did you say? In a given second. That's perfectly. So it's how often something hits you, right? So frequency is right here. So the UV has the highest frequency. Now, here's really testing your knowledge. I've misspelled that free somewhere. There's an E in there somewhere. UE? All right, there we go. Anybody remember the symbol for frequency? It's not the upside down Y. It's not lambda. It's not Q. It's like a crooked, funky looking V. Did you see the V? What is its Greek name? Nu. Okay. Now, high frequency. It's the amount of waves that pass a given point in a second. That's why it's meters per second. Okay. Now, highest frequency. So what does that tell you about the wavelength if it hits you like this? Really, really short. All right. So not only does it have the highest wavelength, it has the highest frequency. It has the shortest wavelength. Now, what was the symbol for wavelength? That's the upside down funky Y, right? What was that Greek name? That's lambda. You'll use that in physics a lot? Okay. Theta and lambda, y'all use nu when you get into optics and stuff like that. Sound, especially. All right. So that is true. So if this is true about UV, what is true about infrared? It's got a low frequency. I'm just going to call this V. And it's got a, what about its wavelength? Very long wavelength. All right. So now that we know that thing, what did they say the color of the solution was again? Red. So what do we know about red in comparison to the spectrum that we see?
It's going to have
It's going to have long wavelengths, low frequency, not very harmful to us, right? I just kind of want to point that out. That's where the red factor comes into this, okay? And so what we're trying to determine from this is the optimum wavelength of red. Every color has its own wavelength. The plot of the absorbance. This is a new thing. This absorbance. You remember when I drew this just a second ago? Okay, and again, what's this thing called that you put the liquid in? A cuvette. And you know you've got light shining through, and then you've got the monitor at the back monitoring how much light comes through. How could you measure the absorbance? Okay. How could you measure it? Can you know how much that exactly took in? The way you do it is you know how much light left, and then what? How much came in. So how could you find how much it absorbed? Subtract the differences. So if you sent out 100 photons and it only took in 20, how many did it absorb? It absorbed 80 photons. Are you with me? So that would give you your absorbance. All right? So again, the absorbance is A versus wavelength lambda. What is the optimum wavelength for this experiment? Which means that the red loves this wavelength. It takes in that color or that wavelength the most. What do you think the answer would be? The highest point on the graph. Very good. It loves that wavelength. Red absorbs that wavelength the most. So what would you guesstimate about the answer of the wavelength? Okay. Well, let's talk about, we know this is 480. 440. This is 480. So what does that make the dotted line? 460. And where's the top of the peak? So you would guesstimate about 450. Everybody good with that? So it says, what is the optimum wavelength? You would definitely say 450, correct? But then what else do you have to do? Justify. Let me show you their key and kind of base it off of that. Oh, that's way too far down. All right, here is their answer. The optimum wavelength is 450. Now, let me ask you this. Where did this thing right here come from? Does everybody see where it came from? So can you just say 450? What is that, 450 purple people eaters? No, you have to be specific. And what is nm again? It is nanometers. Here's another test of your knowledge. What is the unit for, or what is the size of the nanometer? Better remember? Not 6, -9. Match up your 9s. 6 is the micrometer. Okay, 6 is micrometer. So we know 450, but here's the reasoning why. Because that is the wavelength of maximum what? Absorbance. It absorbed that much wavelength at the highest peak. Okay? Go ahead. Again, this is a new topic. The questions are okay here. How did I know what?
Like, how did you know that it's asking, like, I don't understand, like, what it's asking. Can you, like, repeat?
What is the optimum wavelength? All right. So we know that the answer must be a wavelength, correct? Yeah. Well, our wavelengths come from down here for this experiment. So basically what that's saying is, for this particular species of solution, what wavelength does it absorb the most? What does it like the most? It likes the wavelength 450 because it absorbed that at the highest location. Does that help? Okay. Any other questions? So looking at the point clarification, you get 1 point with a correct justification. Is everybody fine with that? Okay. All right. Now, let's go back to this. All right, so here is our next little part. Again, the way it kind of looks on your page is hard. You'd have to flip back or look side by side to figure this one out. All right. A calibration plot. As soon as you see the word plot, what do you think is going to have to happen? Look on the top right. What do you notice? A blank graph. We're going to have to fill that thing in. A calibration plot for the concentration of this thing is prepared at the optimum wavelength. Again, what was the optimum wavelength? 450 nanometers. Okay. The data below given the absorbances measured for the solutions of a set of known concentrations. All right, well, let's talk about this. Real quick, real simple. What is the concentration doing as you go from top to bottom? Is it increasing or decreasing? It's going from 1 to 18. It's increasing. Since all of these are to the negative fourth, what can you really do in terms of trying to compare them? Can't you just ignore them? Do you agree with that? So as the concentration goes down, what is the concentration doing? The concentration is increasing, right? Is that a common? How is it related to the absorbance? As the absorbance goes down, what is it doing? It's also increasing. So how are concentration and absorbance related? Directly related. As the concentration goes up, the absorbance goes up. What does absorbance mean? How much it absorbs. It takes in, it sucks it in, right? And let's talk about how we can know this. The unit for molarity is what? Here's something that I have not said in a long, long time. What is a mole by definition? Perfect. That's exactly right. The mole is an amount of substance. So here's what I'm asking you to do. If I asked you to run to the office right now, would there be anything in your way to get to the office? No. So will there be a whole lot of absorbance, if you will? Can you come back later? Okay. All right. So there wouldn't be a whole lot of in the way. So there's like 0 moles right now. You with me? But then what if I asked you to run during break? Are there more moles in the commons? Yes. So that means the concentration would be what? Higher. So you'd run into more people. So it would block you, which make the absorbance do what? Go up. So does that make sense how this is mathematically related? The more moles you have, the more it can absorb because there's more things in the way. That's kind of what's going on here. All right, so now let's look at the actual plot that we're going to have to do. Draw a Beer's law. Yes, it is Beer's law. We're not going to get into this into great detail, but all Beer's law is capital A equals ABC. Yeah, I know. That is on your formula sheet. What is A, you think, capital A? Absorbance. And I don't really want to get into this because the other thing could take too much time. And to be honest, absorbance. Whatever, you get it. I don't know the full extent of this. This is one of my weak parts because it's a new deal. Draw a Beer's law calibration plot of what? All of the data on the grid below. Where would you get your data from? The table from before. Now, this is where people, and I read through this is where people messed up the most. Indicate the scale on the horizontal axis by labeling it with the appropriate values. What does that mean? So, do you have any numbers down here at all? So, you're going to have to fill them in. So, here's what you need to do. We know that it starts at 0 and it has a certain scale. What is the highest concentration they give you listed? 18. So do you agree that it would probably be a good idea to put 18 at the very end? Okay. Now, here's what they asked earlier. To me personally, what I would do is I would say concentration and then times 10 to the negative fourth moles per liter. Why would I do that? That way they know all of those numbers are applied to that. That way you don't have to write times 10 to the negative fourth on every single one of them. That is appropriate. Does that confuse anybody? Basically, I'm just saying 18 is times 10 to the negative 14. All right. Where was the absorbance at 18? All right. So on this absorbance y-axis, where would I put that? What's that non-labeled line? 0.35, and it was point what? So we're going to say it's about right below that value. Does everybody agree? All right. So here's what you've got to do. You've got to determine how we can break these increments up to get from 18 to 0. Say it again. Did anybody else come up with 3? How did you come up with 3, Keely? Because there's how many lines? 6 lines. Your top number is 18. 6 times 3 is 18. Does that make sense? You could play with it enough to kind of figure it out. So what would this line be? That would be 15. What would this line be? 12, and then 9, 6, and pretty simple, right? Hopefully you could have played with that to figure that out. Now this is the easy part. What do? Go back to the other side and plot your points. All right, what was the next highest? So go upwards from 18. What, it was 18. What was the concentration? So 12 even. All right, so it's going to be right on the line. And what was it? Absorbance. All right, 0.239. So let's just say about right there. Does everybody favor that one? Okay. What was the next concentration? 8. So now, what are you going to have to do with it? It's not on a direct vertical line. Kind of go right to the left of it. And what was its absorbance? 0.160. So where is it going to go? Right above the non-labeled line, right? So we're going to go about right there. Do you have to be perfect? As long as you're in the range. All right, what's next? The concentration. 3, all the way down to 3 on the dot. Okay, what was its absorbance? All right, 0.06. So where will it be? Right above that non-labeled. And then the last concentration, 1.1. So it's right at the halfway part between 0 and 3, or right below it. I take that back. What right below it? And then what was its absorbance? What? 0.03. Well, what is this half labeled line? 0.05. So let's just give it about maybe right there. And what do you notice has formed? Can you just plot points? What do you always do with graphs? Please connect these dots. Now again, none of us are perfect. That's actually pretty dadgum good. I'm impressed with myself. So is this a hard task to do at all? Time consuming, yes. In terms of difficulty, please don't mess that part up. Okay? Real easy to do. You had to know 0 chemistry to do this, didn't you? This is all math. There was 0 chemistry involved in this. Let me just show you their key, just to kind of show you what they did. Is that almost exactly what we did? Okay. Now, their labels at the bottom, they only did 3, 9, 15. I'm going to be honest, I would go the safe way, label everything. And again, if you did what I did with the times 10 to the negative 14th, then that's perfectly fine. So how could you have earned points? 1 point is earned for a straight line plot, and 1 point is earned for a correctly scaled horizontal axis. Well, you wouldn't have known it was a straight line unless you plotted the points. Does that make sense? Okay. All right. Next question. That ion solution, an unknown concentration, has an absorbance of 0.3. Use the plot you drew in part single I to determine the concentration of the solution. This is probably one of the easiest questions on this entire thing. So, we've got it labeled. It said, what was the absorbance? All right, so on the y-axis, it was 0.3. Go all the way over to right here. And what would you guesstimate that the concentration was? 16. But can you write just 16? That is where, if you don't do the times 10 to the negative fourth, you'll mess that up. So 16 times 10 to the negative fourth. Is there any chemistry involved in that? Nope. None at all.
Like, do we have to put approximately or?
C plot blah 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 is approximately 16. If you can't mathematically prove it, I would state approximately. Does that make sense? Okay. Cage, you with me? Good deal. Any questions so far? You better be able to do C single I. Do C single I. Uh-oh. Are you kidding me? Seriously? It's a KC. Sometimes I don't know what y'all's uh-ohs are. Do any of y'all need to be kicked in the shin for missing this one? Mr. Keish? Did you get it right? Look. Okay. Why is there only one thing on top? Products over reactants. Why are there no exponents? No coefficients. Why is nothing left off? They're all aqueous. What's not left in? What's not put in? Very good. Solids and liquids. Some of you left that blank on the mock exam, and that really bothered me. Bad. KC, what is different between KC and KP? The brackets. If you put parentheses here, would you have earned the credit? No. They would mark it wrong if you put parentheses. Did anybody do that? Good. Yes, ma'am. Okay. It was one of the. I remember it was the. It was a Quest homework, and remember you got to think about this is putting it in a digital computer. Sometimes it's hard. No, it's the parentheses around the P with a subscript of the thing. Okay. If you watch the video from yesterday, we do a KP and you can see it. Okay.
Which K is it just products and reactants?
KSP. There's not a denominator in KSP. Okay. All right. Double I. The student combined solutions of FeNO3. Now let's talk about that. What do we know about all nitrates? Soluble. So do you agree that that nitrate has no effect on what we're fixing to do? And K, SCN. Now SCN is just thiocyanate, okay? It's a polyatomic. What do we know about K? Why? Very good. It's group 1. To produce a solution in which the initial concentrations of Fe and SCN, where do we see those already? Do you agree that those are reactants? Okay. Notice what it just said. The what? The initial concentrations are both the exact same value. The absorbance of this solution is measured, and the equilibrium concentration of this one, and where do we see that at? That's a product. Is found to be this value. Determine KC. Who what? Rice table. Fantastic. All right, so let's set up our rice table and do this. You can do it wherever you need to do it. You just need to do it. All right. Matter of fact, I'm just going all right. So we have Fe3 plus SCN is at 1 negative? Negative. In equilibrium with Fe, help me out, SCN 2 plus. All right, so that's what we have. Now, what does it tell you about Fe3 plus and SCN negative? Read the question. What does it tell you? It gives you their initials. Very good. And what are those? All right, 6 times 10 to the negative 3. 6 times 10 to the negative 3. What do you know about the initial of the product? It's what? 0. All right. What is the sign of the change of the reactants? Negative. Negative. What about the products? Positive. What else goes in the C? The X's. However, what else could also affect your C row? The coefficients. Please don't forget that. If there are coefficients, you would have 2x or 3x or 6x, right? Don't forget that part. Now, we have EX, and what do we do there? Essentially, we just bring our math down, correct? So we have 6 times 10 to the negative third minus x. 6 times 10 to the negative third minus x. And then we just have just regular old x. Correct? Yes, ma'am.
You said if it's below -1, you change it.
Just leave it like this for right now. It's shorter to write it like this for right now. But yes, you can if you want to. All right. Keep reading. What does it tell you about FeSCN2+? The concentration when? At equilibrium. Where does that go in? At EF. Very good. So that number is what? This should make you so happy. Because you know what is. You know what X is. Everybody agree? So since you have X, it makes our life so much easier. So if you take this number, plug it in here, the answer you're going to get for both of them is 5 times 10 to the negative 3. So, what was the original question? Solve for KC. Have you already written KC? From your Rice table values, what numbers do you plug into K? So take these numbers. Do you have to rewrite K? No, that's fine. Take these numbers and write it what it would look like as you plug them into K, and I'll give you the answer. You don't have to calculate it up. That make you feel good? You kind of know what to do here? Okay, this is what this is about. Building you some confidence and knowing that, hey, I can do this. I can do a Rice table. Yes, ma'am. You can do squared. That's perfectly fine. Yes, what she just said, since both of these are the same value, you are allowed to do squared. The reason it looks a little different is because we normally see square on top, and this one just works a little bit differently. Now, what I want to show you, just to even build your confidence even more, is look at what the key contained. Is that not almost exactly what you just did? The only thing they don't show is the X part. But what you did is perfectly acceptable. Now, here's the answer. Can you see the dot behind it, the decimal point? Why is that important? Very, very good. Sig figs. Because both of the numbers that we used originally, one was 6.0, the other one was 1.0. So I'm assuming when you calculate this, it's like 40.0 or 40.1 or something like that. So the decimal is very important there to make sure you have 2 sig figs. Huh? Or you could do that. You need 2 sig figs. If you don't have the decimal or the bar, it's only 1. That means it's significant.
Wait, so like you have...
Hang on. Go ahead. The bar just means that 0 is significant. Or put the decimal. There's 2 sig figs. Without it, there's only 1. Is the decimal point present or absent in the one you see? Never mind. Juhi, go ahead.
If you don't do any of that, will it take points off?
How else would you do it?
No, just put 40.
Oh, it depends on if this is the question they do the significant figure point on. I don't know. There's only 1 out of the 7 questions they pick to count sig figs on, and it may be this question. That's why you need to do it for all of them, because it may be that question that they do it for. Okay? All right. Finally, last part. If the student's equilibrium of this solution of an unknown concentration, this is really important, fades to a lighter color. So basically that red cuvette that we sat in, it has faded from the red from the original time. Before the student measures its absorbance, will the KC be too high, too low, or unaffected? Now, you have a 33% chance at getting a point here. Why? Because you can guess. Don't leave it blank. If they give you opportunities to guess, at least guess. Let's take a poll. Think for a second. How many of you think K will be too high if it fades? Okay, I'll give you a second. The solution fades to a lighter color. Think about what KC is based on this reaction. Remember, we're dealing with this thing. If that fades to a lighter red, what will happen to K? How many of you think K will be too high, too low, unaffected? How often do you think unaffected is a possible answer choice? It's rarer than not, but it is possible. If you put a solid, what happens to the equilibrium? Nothing. So there are times where it could be. All right. The correct answer is too low. All right. Very good. So let's talk about why. This is their answer explanation. The value of Kc will be too low. Notice what they just told you though. 1 point is earned for correct prediction. There's your 33% chance. Congratulations. Okay. The lower absorbance reading indicates lower. What does the bracket thing mean? So that means the concentration did what? It went down. So when you wrote your K expression, where was this in the expression? Top or bottom? So the top number did what? It went down. So what did K have to do? It had to go down as well. So since the concentration of that was lower, then it in the equilibrium expression will result in a lower value of K. Does that make sense? Really what happened is when it got a lighter color, the moles became less. Well, there's less things in the way. Does that kind of make sense? Which means less will absorb, so your K must decrease. Any questions there? We all good? Just maybe some confidence builder and ability? Let's try another confidence builder and let's see how well you do with it. Flip over. The species represented above all have the same number of chlorine atoms attached to the central atom. Draw the Lewis structures for all of them. Let's see how good you are. I'm going to give you a chance to draw all of them. I'm only going to give you 2 helps. Number 1, when it's charged, what must you do to the Lewis structure? Brackets, and you got to have the sign. If it's a negative sign, what do you have to do? Why add? When you're negative, you do what with electrons? You gain. When it's positive, what do? Subtract an electron. Why? You lost an electron. See if you can draw these Lewis structures. I can't be there to help you out, and I don't want to do them for you. All right, I'm going to pause the video and kind of give you guys a minute. The bell may ring, work until it's done, and I'm going to try to show you the answers at the very end.